Hello everyone, welcome to another Lessons Learned video. Today we're going to talk about alkyne reactions. Just going to go over some practice problems and explain a little bit about them. If you are completely unfamiliar with them, this might be a good video to start, but I'd suggest that if you're confused, revert to other sources because this is mostly for practice. So let's say we have this starting molecule here. And this is going to be an alkyne. This is what it looks like. You may see in other drawings that it looks like this. These are equivalent. I find the bottom one confusing because you don't quite see the carbons there. It's hard to perceive. So I like having it like this, where there are two carbons here, a triple bond between them, then two carbons at the end. So this is an internal alkene because the triple bond kind of is in the middle of the carbon chain. If you were to have this situation, this would be in terminal alkene. That would be a terminal alkene too right there. So there are multiple ways you could do reactions with these. So let's say that we do a reaction where we react it with H2 and platinum. So this is if you add hydrogens to it. Platinum is a catalyst here, and if you do that, what you're effectively going to get is going to be you had 4 carbons before, 1, 2, 3, 4, and you're going to have 4 carbons after it, and the triple bond is getting rid of, and we added new hydrogens. So we added a hydrogen here, 2 on each carbon. So those are the new hydrogens that we added. Okay, so that's how you make an alkene from an alkyne, or an alkane from an alkyne, really. Right. So if I were to, there, that's better. Now, if you were to react this with H2, and you were to put Lindlar's catalyst, this is a certain catalyst. What it basically does is it makes it so that you can basically add 2 hydrogens to it, but 1 on each carbon. So as opposed to adding 2 hydrogens and getting rid of the pi bonds entirely. We keep the double bond, but this case we're going to actually have a cis product. So the product is cis. Okay. Another important reaction here is going to be sodium and ammonia, right? And so keep in mind that this is elemental sodium. This is not the sodium ion. Okay. This is liquid ammonia as the solvent there. And if you use this as the reagent, you're going to get similar product to this. However, it's going to actually look trans as opposed to cis. So this, you're still adding a single hydrogen to each carbon across the double bond, but it's trans. All right. Now, that's how you basically add hydrogens to this. So let's erase what we just drawn. And you can take a note of this and similar in other reactions or similar patterns as this. So if we were to take this alkyne and add HBr, and let's say we were to add 1 equivalent of it. So for every molecule of this alkyne, we'd add 1 HBr molecule. We're going to get this outcome. We're going to get bromine here, and then we're going to get a double bond and a new hydrogen here. Now, if we were to do the same reaction, but let's say we were to do it with a terminal alkyne and add HBr, but add 1 equivalent of it. I'm going to get an interesting pattern here. So notice how we have 3 carbons here. There's really, you can't see it because of my stuff. 1, 2, 3. So we'd expect in the products we have 3 carbons. And so, but which carbon is the bromine going to attach? Is it going to attach to this carbon or this one? So it's actually going to go on the more substituted carbon, so on this carbon, and the double bond is going to stay there, and the new hydrogen is going to go here. Now, if we had another equivalent of HBr, so HBr again, in this case it doesn't matter if you had one equivalent, if you just had HBr excess, then the next bromine is going to attach on this carbon, so you're going to get this outcome, and you're going to get a new hydrogen on this carbon here, and the old hydrogen is still there. And in the bottom scenario, you're going to get the bromine going on the same carbon as the last bromine, and then the new hydrogen, and the old hydrogen is still there. If you were to add excess HBr, it would go directly from this to this product. Not technically directly, right? It would have this as an intermediate, but it would happen very fast, right? Very quickly it would form to this. But this is the steps by which it goes. It first becomes this, then it becomes this. Now let's say we were to react these same molecules, but we were to basically react them with Br2, and we already used one equivalent again. In this scenario, we're going to get a bromine on each of the carbons. Here as well. Then if we add Br2 again, and we make sure that it's at least one equivalent, we're going to basically get rid of that double bond and form bromines. Bromine carbon bonds all across those carbons that were connected to the double bond before. Now let's say that we were to use the same alkynes, and I don't know why I erased them. It was a bad idea. Don't erase alkynes when you don't need to. Okay, so let's take these again. And there's a reaction in alkenes that looks like this. You add acidic water, and sometimes you might see it as H2SO4. In alkynes, we have a similar reaction, but it looks a little different than this. You add HgSO4, so this is with mercury sulfate as a catalyst, but the main thing that is, technically this is a catalyst too. But this is within a context of a water solvent. If you were to do this reaction, you're essentially adding a hydroxyl group. If you were to do this on a alkene, so it'd look like this, right? If you were to do, it would turn out like this. You'd get a hydroxyl group on the more substituted carbon. And here we're going to get a similar pattern. So the hydroxyl group is going to go on the more substituted carbon. In this case, they're both secondary, so it won't matter. So it'll end like this, but here it will be as such. Okay. Now there's a very important difference between what happens in alkynes and alkenes. Here, this is what we call an enol. So we have a double bond between the two carbons, and we have a hydroxyl that's attached to one of the carbons that's a member of the double bonds. This enol is a molecule that's very unstable, so it's going to actually go through an equilibrium process, and most of it is going to be converted to what's called the tautomer of it. So the tautomer of it is going to look like this. Imagine that these double bonds, these electrons just go away, and they form a double bond here between the oxygen and the carbon. Right? So there used to be, oxygen-hydrogen bond, but this hydrogen, these electrons come in and attack here, and then this whole hydrogen with its electrons comes in and takes the spot of those electrons and it bonds to this carbon. So that hydrogen is now here, right? The extra hydrogen. And that process happens very fast. Right? These enols happen to be very basically very unstable, so we get the ketone form. And similar sort of thing happens here. So try and predict what would happen here, right? In this case, let me give ourselves a little space. We would get a similar outcome. So the enol form is not going to last very long, but the ketone is going to. So this is very important. Don't draw this as the product, right? This enol doesn't last long. That's a very important exception in a lot of these organic chemistry 1 classes. You want to make sure you realize that here. Now let's say we react this with hydroboration oxidation. Right? This reagent is for the BH3 thing, and so it's similar to the ones in alkenes again. So here we're going to add hydroxyl group to one of the carbons. In this case, they're both secondary, so it doesn't matter which one you add it to, and the molecule is symmetrical. So we're initially going to get this, but then guess what happens? This is unstable, and really it does this, right? It's going to go in this direction a lot more often than it's going to go in this direction. It's going to turn into the ketone form. Now, previously what happened was that when we did, let's draw what we did, right? When we did the mercury sulfate solution, we ended with a product, or at least with an intermediate that looked like this, right? We added the hydroxyl on the more substituted position, but here we have hydroboration oxidation, so we're going to do the opposite. We're going to add the hydroxyl group on the less substituted carbon, like that. You can keep that. And then this is going to go through an equilibrium process where, as opposed to turning into a ketone, in this case it's going to turn into an aldehyde, but it's really not any fundamentally different than this, right? This is the same process as this. If I could give myself some space bottom here, there. Like that. Let's go over to the last significant reaction of the alkynes. So it looks something like this. So let's say that we have this alkyne and then the other alkyne. And let's say we react them with ozone. Yeah, let's say we react them with ozone. What would happen here if we reacted with ozone? So if we react with ozone, we're going to get a process called ozonolysis. I pronounce it ozonolysis, but it's ozonolysis. In ozonolysis, you can imagine it this way. Imagine that there's a line breaking the middle of the molecule. On one side you get 2 carbons, so imagine that you have, on the other side you have 2 carbons as well, so you're going to get 2 carbons from one side. So this is 1 carbon, this is another carbon. Now, we can draw them parallel with the original molecule, so like this, right? So this is that carbon, and this is the second carbon. Now at this position, this triple bond is going to turn into a carbonyl group. So imagine that an oxygen comes over here. And then from this carbon, right, we have an oxygen going now. But then we also get an OH group, a hydroxyl group going off of it. And so if you flip this molecule to look normal, you can, and then if you flip the letters so that in the English language we don't see H as inverted, you can see that this is a carboxylic acid. And since both sides of this molecule, have 2 carbons, they're going to look identical. So you're going to get identical products from both sides. But here you're going to get some different outcomes. So here, on the right side, when you have 1 carbon on one side, you're going to get carbon dioxide. And then on the left side, we have 2 carbons. And then on one of the carbons, we're going to have a double bonded oxygen and a OH group. Right? And that's how you do that. That's ozonolysis. Let's do a practice problem with ozonolysis. I want to make sure we don't mess this up, okay? This, make sure you practice this a lot, because there are some tricky questions that with the shape of the molecule can look deceiving. So let's take this molecule and run it through ozonolysis. Imagine again the line separating the middle of the molecule, separating the triple bond. On one side we have 1, 2, 3 carbons. So 1, 2, 3 carbons. And one of those carbons is going to contain, one of the terminal ones is going to contain a carboxylic acid group. So that's one side of it, that's this side. The other side is going to have this shape right here. So 1, 2, 3, 4. 1, 2, 3, 4, right? So I've got everything there. And this carbon over here is going to have a carboxylic acid group attached to it, like that. So make sure that you practice drawing that out with more practice problems, and we can go over a few of them. So this was just one. Let's do a few more. So let's say we have. This is you just draw the triple bond first. So we'll go ahead and try that one. So let me try to do this. From the right side, we have the 3 carbons. So I've got the 3 carbons here, and then there's another carbon at the end there. And this carbon, right, because it's attached to the triple bond, it's going to have the carboxylic acid group on it. And the other molecule, you can see it right there. So we can draw it again. So we got the 3 carbons here that represent these 3 carbons. and then attached to the middle one, to this one, is going to be 2 carbons going straight forward. So 2 carbons going straight forward. And on that last one, on this carbon, we're going to have a carboxylic acid group. So that's what that looks like. I'm not sure why there's a... okay, yeah. That's correct, okay. Let's do another one. What would happen here? What if you were to do ozonolysis here? Here you'd simply get carbon dioxide from both sides of it. So that's pretty simple. Okay, it's a tough one, but yeah, let's make it tougher. All right. So in this situation on the left side, you've got 1, 2, 3 carbons in a straight chain. That's 4 carbons. Okay, that's 3 carbons. And then one of the terminal ones has a carboxylic acid group. And here we have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. We can number this because it's kind of complicated. So 1, 2, 3, 4, and 5. So 1, 2, 3, and many people find the numbering system useful. I probably should have used it from the beginning. But anyway. So in this case, carbon number 3 is going to have a methyl on it. And carbon number 4 is also going to have another methyl on it. And carbon 5, since it's attached to the triple bond, it's going to have a carboxylic acid on it. So that's how we draw the products. So I hope that was useful, and thank you for watching.